So today in section 10.4 we're going to be talking about inscribed angles and polygons, which are inside a circle. First thing we need to do is describe or define what is an inscribed angle. So the biggest thing that we talk about with inscribed angles, the thing that's probably the most important thing to remember in defining an inscribed angle, is that the vertex is on the circle. And this is different from the other angles we looked at. We looked at a central angle whose vertex is at the center. So here's my inscribed angle, angle B. You'll notice that the vertex of angle B is right here on the circle. And then the sides of angle B are chords right here, BA and BC. And the arc that this angle intersects is this arc right here. So when we say that an angle is intercepting an arc, what we're saying is that when the angle passes through the circle, right, you can almost envision that these guys right here act as like knives, right? A knife and a knife, and they are cutting the circle into two arcs, right? So you've got this arc right here, which has been cut by those two chords. So that's what we mean by the intercepted arc. So when we look at theorems today about intercepted arcs, that's the arc that we're talking about. Okay, so this is a theorem which now tells us about the relationship between the measure of the angle and the measure of the intercepted arc. And we had a theorem like this earlier in the chapter, but we were using central angles. So now we're using inscribed angles. So this theorem says that the measure of the inscribed angle, so the measure of the inscribed angle is half, 1/2 the intercepted arc. Okay, so here's the angle right here, angle D. There's the inscribed angle. And what we're saying is that this angle, angle D, should be half of whatever the measure of this arc is. Okay. So if we just try to come up with any old silly example, we might say something like, if this arc was 100 degrees, then the angle should be exactly half of it, and that would make this angle 50 degrees, something like that. So let's take a look at a couple of examples. It says, find the measure of each in the picture. So one of the things that I want to notice in this picture is that I've got two inscribed angles, right? I've got this inscribed angle right here. Oops, let's go back a slide. I've got this inscribed angle right here, DEG, and I'm noticing that this is 40. And if I'm applying the theorem that says that the arc is twice the angle, then it should make perfect sense that this guy would have to be twice 40 or 80. So arc DG is 80 degrees. So I can also work this theorem sort of backward. So now let's take a look at this scribed angle, right? We've got this angle right here. That's EGF, and we're noticing that EGF is intersecting arc EF. So again, we can use this theorem to work backward. We know the arc is EF. We should be cutting that in half and finding that this angle right here is half of 58, which is 29 degrees. Okay, so here's a theorem that's relating two inscribed angles to each other. So this says that if two inscribed angles of a circle intersect the same arc, then they should be congruent. And this is really just a follow-up on the last theorem that we just looked at, because you've got an inscribed angle, DAB, and you'll notice that it's intersecting arc AB. Right? So again, so I could say in this example, if this is 100, then of course ADB would have to be half of 100, that would have to be 50, right? But I might also notice that in this circle, I also have arc angle ACB. Let's just get rid of this guy for just a minute. So looking at angle ACB, I'm noticing that angle ACB also intersects our arc AB, right? It's across from this 100-degree arc. So using the theorem that we just talked about, that an inscribed angle is half of the intersected arc, then angle ACB would also have to be 50. So it makes sense that these two angles here are going to be congruent to each other if they're intersecting the same arc. So let's use this theorem and see if we can solve for a couple of things. So looking first at example number 1, I hope you can see that you have this arc, which is intersecting this angle, which is intersecting this arc, and then you've got the same exact arc intersecting angle ABC. So that means that these angles have to be congruent to each other, and that means that X has to equal 81 degrees. Okay, all right, we've got a very similar thing happening in this one, right? Here's your inscribed angle. It's intersecting arc AD. Therefore, this angle, which is also intersecting arc AD, also has to be the same measure, and that means that angle B would have to be 68 degrees. Okay, last one here. So here we go. There's my inscribed angle intersecting arc SQ, and that means that SQ is twice 51, so it's going to be 102 degrees. Okay, so now we're going to look at this angle. Angle SQSXQ now is a central angle. Right, the vertex is at the center T. And for central angles, their measure should be equal to the arc. So that means that angle SXQ is going to be equal to 102 degrees. And that means that X, this angle right here, is equal to 102 degrees. Okay, so we've looked at what happens when you inscribe an angle inside a circle. Now let's look at what happens when you inscribe a polygon. So the word inscribed is basically to draw something inside so that it's completely contained within the circle. So you have an inscribed polygon when all the vertices lie on the circle. So in the last definition, we had an inscribed angle when the one vertex of the angle was on the circle. Now you've got a polygon which has many vertices, and we follow the same pattern. We want all the vertices to be on this circle. So we've got inscribed. And then we've got another kind of a strange word here. We've got the word circumscribed. And circumscribed is actually defining the circle. So circumscribed is really two words together, right? Circum, which means to go around, and scribed, which means to draw or write. So we're talking about the circle is being drawn or written around the polygon. So one of the definitions is describing the thing that's inside, that's inscribed. And one of the adjectives here, circumscribed, is describing the circle, the one that's being drawn around the outside. So over here on the right, we've got a couple of examples of some different polygons that can be inscribed in a circle. We've got a triangle can be inscribed in a circle, and we've got rectangles which can be inscribed in a circle, and we've got even pentagons or hexagons can be inscribed in a circle. you can put all kinds of different polygons inside a circle. And they don't have to be regular polygons. They don't, they can be irregular, but you'll see we often work with regular polygons. Okay, so we're going to look at what happens when you inscribe a right triangle into a polygon, right triangle polygon into a circle. It says if a right triangle is inscribed in a circle, then the hypotenuse is the diameter. So that's one important part of this, okay? It's a right triangle and it's being inscribed, then the hypotenuse is the diameter, right? And this should make perfect sense to us because this guy right here is an inscribed angle, right? And this is a right triangle, so this is 90 degrees. And if we're using our theorem from the beginning of class today, then that means that this right here should be twice 90, or 180, making AC, arc AC, a semicircle, and making chord AC a diameter. So looking at a couple of examples here, I noticed that this guy right here is a diameter. That means that this is a semicircle and equals 180 degrees. And since we have an inscribed angle, WXY, which is intersecting 180 degrees, then angle WXY should equal 90. So now we can set 5x equal to 90, and we get x is equal to, let's see, what do we get? 90 divided by 5x, and we get x equals 18. Okay, let's take a look at part B. Okay, so DE has to be a diameter, right, if we're applying the theorem. So if BE is a diameter, then that makes this arc a semicircle, so this is 180. And they've already given us that all of this is 120. So what remains to be solved for is this arc right here. So we can do 360 minus 180 minus 120 equals x. And as we solve this, we're going to get 60 degrees. All right, last theorem here, inscribed quadrilateral theorem. Again, this is just kind of applying the theorems we've used so far. This says that if a quadrilateral is inscribed in a circle, then the opposite angles will be supplementary. Okay, so that means that this angle and this angle should add up to 180 degrees, right? So if I call this guy x, then this guy should be 180 minus x. So I'm not saying they're congruent, I'm saying that they're supplements. And the same goes for F and D. Right? If I call this y, then this should be 180 minus y. And this theorem is biconditional. Okay. So D, E, F, and G will lie on the circle, right? So the vertices will lie on the circle if and only if the sum of the opposite angles equals 180. So taking a look at example 4, we know these two angles add up to 180. And we know these two angles add up to 180. And I could use this theorem to solve both for A and B in that case. Okay, let's take a look at this one. We know that these two angles add up to 180. And of course, we could solve very easily for angle x here. Okay, so I'm going to post this construction in the School Loop calendar and as a video, and I want you to just go back and watch this video later in the calendar. Okay, last couple of examples are applying all the theorems together that we've looked at. You can stop the video now and go ahead and try all of these examples, and we will talk about these examples when we meet again next time. So again, look at example 5, work together in your groups, practice applying all the theorems that we talked about today for A, B, C, D, E, and F.